Hi everyone, and welcome to online lecture number 6 for this course. Today's lecture is going to be a little bit different because, as you guys know, you guys have an exam coming up next week. This exam will be a take-home exam, and you will have the entirety of next week to complete it. This is not a 24-hour exam, it is not closed notes. You will have full access to all of my YouTube videos and to the internet, and you will have plenty of time to complete it at your leisure. That being said, I still think it's useful at this point in time to do a little bit of a recap. Specifically, I want to focus today on derivatives. Now, we didn't cover any derivatives in the online videos for this course so far. All of that was done before spring break. So that's one reason, that's probably the first and perhaps most important reason, why I think I should be covering some more of derivatives today. The second reason is that derivatives will be the main focus of next week's exam. The third reason is that derivatives are obviously a very important and key part of calculus, and I think now is a good time to go back over and tie together all the different pieces of that topic. Okay, on the screen I've already put up the three main chapters of the book that cover derivatives, as well as what I view as being the main focus of each of these three chapters as far as you guys should be concerned. In chapter 2, we first defined the derivative function, and we went over various different interpretations that we could make of the derivative. In chapter 3, we almost exclusively focused on derivative rules. That includes the power rule, the exponential rule, the logarithmic rule, the product rule, the quotient rule, and the chain rule. In chapter 4, we went over various applications of derivatives, specifically focusing on optimization. Okay, I'm going to go over each of these individually, but I think it's important to leave them all out here to see sort of how we progressed through this course. Okay, let's start with chapter 2. Chapter 2 covered the definition and various different interpretations of the derivative. Now there's a good amount of stuff from chapter 2 that I'm not going to focus on. And I think it's important to be able to sift through the important stuff as far as you guys are concerned, and the more, shall we say, background information that is not going to be quite as relevant on the exam. So what I'm going to do here is just say exam focus. On the exam, I will be focused on making sure that you guys understand the geometric and the quantitative interpretations of the derivative. The other thing that I might very well focus on is the relationship to business. Specifically, we saw marginal cost, marginal revenue, and marginal profit, or profit margins. All of these things relate to the derivative, and it's important for you guys, I think, in this course to not only understand derivatives from a mathematical perspective, but to see how those tie in with real life and with various different applications, and this course's focus is mostly on business. Okay. So these are the focus points of chapter 2, but this is a recap lecture, so I'm going to go back over roughly what these tell you. So first things first, definition and interpretation. And interpretation. And there are several of these. First off, The derivative is the instantaneous rate of change. Of a function. That is the first way to define the derivative, or the first way to interpret it. And I think of this oftentimes as a more quantitative interpretation. On the geometric front, the derivative is the slope of the tangent line to the function at the given point. These are the two primary interpretations of the derivative. Now, when I say that these are the primary interpretations of the derivative, my hope as your instructor for this course is that whenever you work with a derivative, whenever you see the word derivative, or whenever you see a problem that discusses the instantaneous rate of change of a function, or a problem that talks about the slope of the tangent line, that you tie all these concepts together. Remember, these are all one and the same. I know that these ideas may seem different from one another, but they actually all complement each other and tie in with each other. The derivative is the instantaneous rate of change. It is also the slope of the tangent line. It turns out those are the same thing, and they are captured by the derivative. Now, in terms of business, derivatives represent margins. And these can be margins of profit. These can be margins of revenue. These could be margins of cost. And basically what these tell you is they tell you the amount of extra cost slash revenue slash profit earned or incurred for one extra unit produced. So instead of telling you how much total profit you've made, how much total cost you're making, you are paying, how much total revenue that you are receiving, the margins, which are represented by the derivatives, tell you at this amount of goods produced or goods sold, if you produce one additional unit, how much extra cost, revenue, or profit are you earning or incurring? That's what the derivative tells you. Now, I know that at the moment, we are in some strange and stressful times. But I think that one way to use and understand calculus is to see if it can help you understand a little bit what's going on in the modern world. So I think it's also helpful to relate this to coronavirus. For a virus, you have various ways of tracking. You can track total cases. which is quite standard. Or what you can do is you can track current trends. In other words, let's say daily increases. If you do the latter of these two, by tracking these daily increases, these will be, in a sense, very close to our idea of derivative. This is the general idea of derivatives in general. Instead of looking at a grand total, you are looking at what is happening right now. How are things changing at this very moment? And you can tell a lot of things about a certain situation just by having that information. You can use it to approximate in a very short term where you're going to be in, say, 1 or 2 days based off of the current daily rate. This is one of the ways in which very simple forecasting can be done for, say, predicting the current spread of the virus. There are also other ways that derivatives can help with this, which we will get to a little bit later. Okay, I want to reiterate once more, because I think that this cannot be overstated, that even though I list a great number of different interpretations here, these are all capturing the same basic concept. Please, please, please do not view these as different, separate interpretations that are disconnected from one another. All 4 of these interpretations are related to one another. They are all sort of different sides of the same coin, and I think that you will do your best job of understanding this material if you try to view how these different interpretations tie in with one another, rather than learning them separately or just memorizing them for some future benefit or for a quiz or exam. All of these things are what is going on. They're all happening sort of simultaneously. They're all different ways of viewing the same type of issue. And hopefully if you can get these, hopefully you can also start to see how derivatives could apply to other situations or applications than the ones that we bring up in this course, or that I could bring up off the top of my head. Okay, the next topic I want to go over, we did not cover earlier on in this course as part of Chapter 2, but the book does place it there. And I think that when you're talking about this in the sense of a recap or of a review, this is where this topic belongs. And the topic I want to discuss is the second derivative. Now, if you look at all of these ideas and interpretations of the first derivative, you'll see that all of these capture some notion of speed. Speed ties all of these things together. The speed of the spread of a virus, the speed of your cost or revenue or profit, is the same thing as the speed or slope of a graph, which is the same thing as the instantaneous rate of change of a function. That's the same way as viewing it as just a speed. All of these capture the first derivative. So in other words, if you only take the derivative of a function once, this is the information that is being captured. Now, let's look at the second derivative and discuss what does the second derivative mean. Now, from a very simple perspective, if the second derivative is the derivative of the derivative, then you can think about it as the speed of the speed. In other words, the second derivative tells you the acceleration of a function. One way I like to think about this is that this tells you whether the function, and not just whether, but also and how hard, the function is pressing on the gas or on the brakes. Now this is important to think about it in these terms. When you're pressing the brakes, your car is still moving forward. Your speed is still positive. However, it is starting to go down. So even though your car is still making progress distance-wise, it is doing so more and more slowly. That is what it means to be pressing on the brakes. That is what it means for the acceleration to be negative. That is what it means for the second derivative to be negative. If your car is speeding up, then you may not be going particularly fast at all, but it does tell you that your acceleration is high. That is what it means, again, for your acceleration to be positive. That is what it means for the second derivative of a function to be positive. Okay, we'll come back to a lot of these concepts later on in this video, but for now, that's all I want to say about Chapter 2. Okay, let's move on to Chapter 3. I'm not going to have quite as much to say about Chapter 3 in this video. The reason for this is that I think that the most helpful and useful way to go over these notions are in my example problem videos, so you can learn and see more about these rules in those. I do, however, want to do a quick overview of all of the rules that we did cover in Chapter 3. And I split these up into sort of two categories: the elementary rules about specific types of functions, and the combination rules, which tell us how to mix and match those together. In the elementary rules, we have first off the power rule. And the power rule for derivatives tells us that the derivative of x to the power n is equal to n times x to the power n minus 1. That is what the power rule tells us. Then we have the exponential rule. The exponential rule is very, very nice. It tells us that the derivative of e to the x is equal to e to the x. And last but not least, we have the logarithmic rule. And the log rule tells us that the derivative of the natural log of x is equal to 1 over x. These are the three elementary rules that we saw in this class. At this point, I do want to mention that there are elementary derivative rules for all of the standard trigonometric functions as well. So if you know about sine, cosine, and tangent, and all of those related functions, then you should know that there are rules that exist for those ones too. We did not cover those rules in this class. No trigonometry is covered in this class, and you do not need to know them. However, I think that it's useful and important for me to mention that they exist, and you can find them online pretty easily if you ever need to. Okay, those are the three elementary rules. There are 5 combination rules, of which 3 are particularly important. The first is the constant multiple rule. The constant multiple rule is very simple. It tells you that the derivative of a constant times your function is equal to the constant times the derivative of the function. In other words, like I like to say it, constants pull out of derivatives. Okay, the second rule, that is combination rule, is what I call the addition rule. And the addition rule states very, very simply that the derivative of a sum is the sum of the derivatives. Okay, these are the two most straightforward combination rules, and these are the first two combination rules that we saw without doing much of, without causing much of a hubbub when we did. Then there are the three major rules. The first of those is the chain rule. The chain rule is extremely important. I have already made a example problems video about the chain rule, and you can refer to that one for more specifics. What I'm going to do here is just write out what it tells us. The chain rule tells you how to take the derivative of two functions nested one inside of the other. And it tells you that if you're doing this, you're going to get the derivative of the inside function times the derivative of the outside function into which you plug in the original inside function. This is what chain rule tells you. This is the way that you are going to use it, exactly as written. Then we have the product rule, which, as its name implies, tells us how to deal with taking derivatives of two functions multiplied one by the other. And it tells you that that is going to be equal to the derivative of the first function times the second, plus the derivative of the second function times the first. Last but not least, we have the quotient rule. And again, as the name implies, the quotient rule tells us how to take derivatives of cases where you have one function divided by another. And the quotient rule tells you that to find the derivative of f of x divided by g of x, you have the derivative of the top function times the bottom function minus the derivative of the bottom function times the top function. All of this divided by the bottom function squared. Okay, I know that this is a pretty crowded table and a pretty crowded screen, but these are the, I guess, 8 rules that we covered in Chapter 3. You guys all need to know every single one of these rules, know how to make them work for any given problem, know how to pick which ones you need by looking at a problem, and you guys should hopefully all get to the point where you're comfortable doing all of the above. I have several different, in fact the majority of my example problem videos cover how to use and how to identify which rules you need to use in any given situation. Please, please, please refer to those, not only to help yourself with the homework sets, but also to give you guys and to give yourselves an idea of how I expect you to write out your responses when showing your work on the exams in this course. Okay, that's about all I have to go over for Chapter 3. Let's move on to Chapter 4. Okay, Chapter 4 covered optimization and applications of derivatives. This chapter might have seemed somewhat complicated or confusing when we first covered it, or even up to more recently as you're working on problems about it. But this chapter is pretty important in my view. First of all, it gives you an idea of various different types of problems that you should be able to solve for this course. what the sort of classic examples are, and all of that. But I think more importantly for you guys, this chapter really sort of explains, and I guess even if it doesn't do the best job of explaining, it definitely illustrates the reasons why we care so much about calculus and why calculus is so useful in everyday life. And the point that I'm sort of going to focus in on here is this idea of optimization. And I'm going to relate this back to some of the things that we learned in Chapter 2. So from Chapter 2, we know that derivatives tell us whether a function is increasing or decreasing. All right, this seems like a very, very simple idea. And it is. It is very straightforward. It means exactly what it sounds like. It tells you whether the function is going up or going down. But there's a key realization that goes on with optimization problems. And I mentioned this in class when we went over this in the lecture, but I want to reiterate it here because I think this is a very, very simple and common sense sort of fact. But it's crucial to understanding the way that optimization problems work. And this fact is as follows. The top of a smooth hill is flat. Similarly, the bottom of a smooth valley is also flat. I'd really like you guys to take this idea in. I know that this seems very simple. Perhaps it seems so simple that you're not entirely certain what I mean by this, but this is actually a very, very simple fact. If I draw, say, a hill and a valley in a smooth way, then you'll notice that at the highest point up here, we have a point at which our function is completely flat. And similarly, at the lowest point down here, the function is also completely flat. The only condition that your curve has to satisfy for this to be true is for the curve to be smooth. Smooth just means no spiky bits. Nothing pointy, nothing spiky. As long as that's true, it turns out that this will always be the case. And this should make sense. Why do I say that? Well, let's say that it wasn't flat. Let's say that you had a smooth curve, and let's try and draw this here. Here we go. Let's say you have a smooth curve, and you're going up, and you want this to be the highest point. But let's say that you wanted to prove Gabe wrong here. Let's say that you want to be like, no, Gabe, I bet I can find a way to draw a smooth curve whose highest point is not flat. And so you want, at this highest point, the curve to still be going up. Well, then the issue is that if you're going to keep drawing this curve, if you move one further to this side, you will get a higher point. And the reason for this is that you are still going up. So obviously your highest point wasn't the highest point after all. The only solution to this is to either make a sharp decrease afterwards, which results in a not smooth curve, or to have a flat point when you reach your maximum or your minimum. All right, once again, I know that this is kind of silly, but this is the key idea behind optimization problems. What this means is the following, which I will write in red. This means that highest and lowest points have derivative equal to 0. In other words, they are flat. I write this out in red, even though red is harder to see, because this is very, very important to make this idea stand out from the rest of what I'm writing here. If you remember this fact, then you can hopefully reconstruct just from this what the idea behind all optimization problems is. The idea is simply that if you're looking for the highest or lowest point on a graph, you just have to look for the points that are flat. That's all there is to it. That's the entire idea. And I really want to emphasize that when I say that this is the entire idea, I'm not kidding. But how does this reflect itself in a math problem of the sort that I'd give you guys on, say, the exam of next week? And what does this mean by optimization? Optimization is the search for the setting that either minimizes or maximizes a quantity of interest. You have some sort of investment that you are trying to either make as large as possible or as small as possible. Maybe you're trying to do the homework for this course in the laziest way possible. In that case, you'd be doing an optimization problem where you are trying to minimize the effort that you need to put in. Maybe you are trying to maximize the grade you get in this class. In that case, you are doing an optimization problem where your quantity of interest is your grade and you are searching for a maximum. Any situation where you're trying to either get the absolute largest value or the absolute smallest value of some quantity that you care about is an optimization problem. In other words, in an optimization problem, you are looking for maxes or mins. And what is the idea? The idea is look for flat points. That's it. That's all there is to it. That is the entire strategy that we have behind doing optimization problems. Well, I lied. Remember that smooth thing? That smooth issue? That adds a little thing. It could be flat points, or maybe spiky ones. Why do we look for spiky ones? Because remember, that's where our little factoid breaks down. If we have a spike, then we can't really use that important fact, so we have to look for those as well. I put it in parentheses because in many cases in this class, we don't really look at functions that have spikes at all. It's not very frequent. We like to look at very simple functions. So for the most part, you're just looking for flat ones. It's a little bit of a lie because spikes count as well. Now when I say look for flat points, the reason why this is successful is that the maxes and mins must be among them. Think about this a little bit like a sort of lineup. When you draw a graph, you have an infinite number of points. All right? If you tried to search through all of these one by one, you would never get anywhere unless you were somehow incredibly lucky, and if you were that lucky, you would be winning quite a few lotteries. So instead, the strategy is to avoid looking at points willy-nilly one by one. Instead, the first thing that we do is narrow down our search to just trying to find points which are flat, or if those exist, points where there are spiky bits. Once we've found those should usually be a pretty small number. Small as in not infinite. If it's not infinite, we can actually count through them. And moreover, in most practical situations, not only will it not be infinite, but you'll only have a couple of these at most. And the big idea here is that since maxes or mins must be either flat or spiky, then if you found all of the flat and spiky points, then the maxes and mins must be among them. You know the culprit is there somewhere, and the culprit is one of those few suspects. Okay, this is the key idea. That's the whole point. Now, if we're talking about a graphical optimization problem, this is all I have to say about this. There's nothing more to be done. You're just looking for points on the graph which are either spiky or which are flat. It's worth noting that spiky and flat points are called critical points. Seriously, that's all that word means. The word critical points just means points that are either spiky or flat. That's all it means. It's not any more complicated than that. It's not some fancy, very complicated mathematician-only idea. It is something very straightforward. Okay. Let's give myself a little bit more room here. And discuss what we have to do if we're not in a situation that's just graphical. Again, these ideas refer to the graphs. Okay? These are always valid ways of thinking about the problem. These are just the graphical interpretation of the ideas here. If you're trying to relate this to the formulas, then the idea is still the same. There is nothing different here. The idea is look for inputs where the derivative either is 0, those are the points where it's flat, or does not exist. Those are points where it's spiky. This is the entire plan as far as tackling optimization problems in the land of formulas lies. The entire goal is basically to solve f prime of x is equal to 0. And also when does f prime of x not exist? If that's relevant, you need to do that too. But for the most part, the goal of optimization problems is to find critical points by solving f prime of x is equal to 0. Points where the derivative is 0 or where the derivative does not exist are called critical points. It's the exact same thing as points where the graph is flat or where it is spiky. These ideas, again, are one and the same, and hopefully when you think about these, when you try to solve problems related to this stuff, you think of both of these facts together and related to one another. Okay, there are a couple other ideas that are also discussed in this chapter. And I don't have the time, this video is already dragging on pretty long, I don't have the time to go over all of them, but I do want to come back to our earlier discussion of the second derivative. We mentioned earlier that the first derivative tells you whether the function is going up or down. The second derivative tells you instead whether the function looks like an upwards U, which we call concave up, which by the way means it is speeding up, or whether the function looks like a downwards U, which we call concave down, and which, for the record, tells you the function is slowing down. That's what the second derivative tells you. When it's positive, that means your function is speeding up, it's concave up. When it's negative, that means your function is concave down, which means it's slowing down. If you solve f double prime of x equals 0, you can find inflection points. Inflection points are where you pass from one of these to the other. So you go from upwards U to downwards U, or from downwards U to upwards U. It also means that you go from speeding up to slowing down, or from slowing down to speeding up again. The idea is exactly the same as all the stuff for first derivatives, but we're talking about a slightly different quantity. I want to mention this because this is relevant, and because, just like in chapter 2, we discussed everything from the perspective of first derivatives and then mentioned second derivatives, I think it's useful to do the exact same thing here in chapter 4. Okay, a quick word on applications. I mentioned earlier that applications are the main focus of optimization. If we're trying to optimize something, that means that there's something in real life that we care about enough to try to sort of find the minimum or find the maximum for. There's a lot of different applications that can be relevant here. A lot of them relate to business. So in business, you might want to maximize profit, or revenues. You might want to minimize costs. You might want to minimize operating hours. So especially if you're running let's say in current times with the virus going around, if you are running a business that provides an essential service, but you want to still take care of your employees and reduce the risk of infection, you might want to minimize the total number of operating hours that you use in order to accomplish your essential task. This can be relevant in situations like we have right now, and doing this is also an optimization problem. Now, there are various other situations in which there might be optimization involved. And these things can include various situations in biology, physics, etc., some of which are actually natural processes. So, for example, if you're talking about an animal hibernating, hibernation optimizes efficiency of calories. Right? Food is scarce in the winter. So by hibernating, animals can make the best use of the amount of fat and of food that they have available to them by minimizing the amount of activity that they do. This optimizes their rates of survival. You might want to optimize the amount of chemical compound produced in a reaction or some other lab setting. Again, to relate this back to, I guess, the current events, but also any other scenario that is a medical scenario. If you are trying to test somebody for some sort of compound in the blood, then you are actually going to try to do this by using the smallest amount of blood from your sample at any given time for the tests. When you're taking or receiving, for example, a full blood panel, that means that from those vials of blood that are being drawn from you, many different tests need to be run to test their various, say, quantities or concentrations in various different compounds and all that stuff. Sometimes upwards of 10, even 20 different tests are being run all off of a single sample of your blood. When this happens, they need to devise processes that will optimize the amount of results or the effectiveness of their results that they can receive, while minimizing the amount of the sample that they need to actually use up whenever they do these tests. Usually, they cannot use the same sample or the same actual blood for all of the different tests, so they are operating in a sort of limited spectrum here. All right, there are many other settings in which optimization is relevant. Some of them may show up in agriculture, others may show up in really any specific type of industry or business. Some of them may even show up in your leisure activities, whether they are sports or any other type of thing that you may do as a pastime. Oftentimes, there will be some sort of optimization going on that you're looking for. and all of these can be viewed sort of from the spectrum of mathematics. Okay, I wanted to end today's lecture by discussing something in advance of the exam next week. And this is the fact that, as you guys well know, I've been putting out a lot of videos on example problems and things like that to try to help you guys out. And I want to start off with a note. I've already said this several times, but the videos on example problems are to help you guys. I also want to note that they are also your guideline for showing work. Although I should mention here that color coding is absolutely not necessary unless you want to. I have some additional example problem videos coming up, including one on optimization problems that I owe you guys before next week's exam. But even with that said, I wanted to mention to you guys that I am taking requests. I like to think that I have a pretty good idea of which topics are difficult and which ones are more easy for you guys. I like to think that I have a good idea of what you guys would like me to cover in more detail. But that's not always true. You guys know best what you need from me. I can't meet you guys in person. What I can do is receive emails from you guys. If you have any topic that you would like me to make an example problem video about, let me know by email and I will try to get it done as soon as possible. Just let me know by sending an email to my address, which is gstaton@email.sc.edu. Just email me there, and I will do my best to not only answer any questions you might have, which, by the way, I will be doing throughout next week during the exam times. You guys can ask me questions about problems while you take the exam. I won't give you answers, but I will help explain any issues you may be having. And again, I am taking requests for example problem videos. If there's anything you guys would like me to cover in more depth, just let me know. Shoot me an email to this address, and I will get on it as soon as I can. Alright, that's all I have for you guys for today. As usual, I hope you guys are all staying safe and healthy at home. Best of luck on the exam next week, and I'll see you guys next time. Bye-bye.